one sentence. So Sean, I believe, and I guess also Roger, I guess it was Sean who approached me with this idea. He's interested in occupancy of buildings. And then in parallel, Kavya, I believe, a semester ago said she wanted to focus more on maybe something that includes hardware. And so we thought of a new pilot sub-team on sensors for buildings and how occupancy could be measured in maybe novel ways. And so this is the first semester on this. I'm very excited to see where you guys are. Yeah, please take it away.
Okay, so basically our research will be decision-relevant occupancy information for room scale or zone scale HVAC operation. So more specific on the typology sensitive framework for the minimum occupancy information that for the design process or in the operation. So the background is like the building performance gap is kind of multifactorial. It's not just an equipment problem. So also what happen in the room, like the occupancy operation and the air quality is random and it's gonna be biggest driver for in the real use and making the performance gap between the simulations. And also, especially the human-related factors will be influence the building energy use as much as even the physical factors. So it's gonna be a big problem for what we in the real operation. So the current HVAC operation is still rely on the simplified occupancy assumptions, that statistic mode assumptions for the activities for the equipment load, and also like just setting a consistent density or a fixed schedule. But the real using is gonna be a more dynamic. You don't know people when they arrive, departure, and maybe they just do a short break, but the equipment is still on. Also, the spatial distribution gonna be different. People probably not gonna be sticking the exactly same time every time. Also, from the behavior pattern, we will have different like metabolic peak and stuff from human. But if we put all the information to the system, are gonna be just makes the HVAC system more confused because they're just too much. So the issue is not just missing data alone, as it will be oversimplified representations. So based on that, well.
So I do have to try to. Okay. I don't know. Oops. Try now.
Okay.
So I need to have my mouse pointer on the slide, otherwise.
Yeah. So basically, from the previous research, definitely they already know like the occupancy uncertainty gonna be drive a very large simulation error of gaps. And also the occupancy-based control can save energy while it maintains the reasonable comfort rate, like the standard they have as over 80s. So I mean the main question gonna be like in the real use in practice level, how do we influence their decision making, right? So it will be what kind of minimal set of occupancy information is sufficient to meaningfully improve the room scale HVAC decision under the different spatial context and the operational context. So basically, from the gap to the thesis, the previous working is still mainly on the sensing centered, but we are moving to the decision centered to trying to create some novelty from that way. So we are going to find out the main marginal value between each occupancy layer, that decreasing or increasing by like components. And also we're going testing the minimal sufficient information for different scenarios. Also, it will be a kind of reproducible pipeline, also like a framework for the testing for room. So it's an outline for our like the whole thing. I mean, start from the hardware sensing, we collect the data and go into a pre-processing to abstract all the information into the schedule that the simulation can understand, and we will create different generations scenario that input for the simulation. And then under a controlled comparative simulation, we will have a kind of accuracy result, and then we do evaluation on it.
So first, for how we will acquire the occupancy data, we're using a thermal camera. It's called the MLX 9640. Doesn't really matter too much, but basically what it does, it's going to be installed on the roof of a room, and then it has a pretty wide angle, and it picks up in a pixel array the temperature sensors. If go to the next slide, you can see a little better, but it picks up temperature sensors of each location and outputs it just as like an array of integers of what that temperature it's sensing is. And essentially, the way we're just gonna do it is take the ambient temperature of a room, and humans are around 5 degrees hotter usually. So you can pinpoint, like using a bounding box, just figure out the pixel locations of where a human most likely is, and then figure out the midpoint of that and say that there's a human there. So this one, for example, just picking up one human, and it gives you output and just like the number of humans and then whatever XY coordinates of each humans are going to be. And the idea that the reason we want to use this is because it's not going to pick up like any faces or anything, so it's going to be pretty private. And it also tracks in a lot less data than you would have if you use a camera.
Is this one human standing static?
Yeah, but this is from a top view, so it's like they're like kind of like, I think this was when my friend was like kind of like raising her arms.
And is it, okay,
Yeah.
is it, okay, I see. And dynamically, how quickly does this update? If they walk through the room?
It's pretty fast. I forget the exact refresh rate, but it's like in milliseconds stuff.
Okay.
Yeah.
Very fast.
But sometimes the temperature of a spot, if a human walks through it, that can actually take a little longer. So more than the camera, I noticed that was updating a little slower, but it still should be quick enough for our purchases.
Okay.
Yeah.
Mhm.
And then for the installation specifically, we're gonna have, this is like an approximation of our room layout, but we can use 4 cameras to basically cover the entire room layout. And on the right, it's just an example of like how it would look like. And you would just pick out, like, these are humans there, these are locations. And then the final version, so this is like the prototype I've been working with. Ideally, when we actually go into it, I'll like solder it up so that it won't have any fuse contacts, but we'll just have a couple of ESP32s spread across their microcontrollers that get in the data from the cameras, which is like the little sensor on the left. And it'll store all the data on an SD card that we can just take out and then plug it back into our computer and then get all the data. And it'll just be connected to a wall. We're getting.
This ESP, is this a Wi-Fi thing? There was this, or is this a different?
Oh, no. You could have this
Yeah.
like connected to Bluetooth or Wi-Fi.
So for now, it's offline. In order to look at it, we would have to read the SD card.
Yeah.
Unless we get a different ESP that has Wi-Fi.
No, this ESP32, you can also put Wi-Fi on it. But
Okay.
for our purposes, I think since we're like probably like have like a session where we have the data collection happening, I think it may make more sense just because with the amount of ESP32s, we have to start off with an SD card.
Mm.
But we could also probably transition to Bluetooth or Wi-Fi too.
Okay.
Yeah. But yeah, these do support that.
So based on the calculator from Capella hardware part, so we can achieve the different hierarchy of our occupancy information. So from the level 0 gonna be a baseline, it will be a schedule, fixed schedules. Level 1 will be a person's binary occupant, unoccupant. Level 2 will be the whole room head count. Level 3 will have the spatial distribution since it's a camera. So we could be different, like we could zone sitting areas, working station, or like a subzone, stuff like that. And level 4 gonna be the activity, so basically performance, like basically the behavior patterns. So we will mapping from the spatial distribution for like the people behavior, and then we will have the more accurate human metabolic on that. So for doing that, it's basically because the more information is not equally to the more valuable. So the value depends on the control objective, spatial context and the deployment burdens. So it's depend on how they're gonna design, how they're gonna operation the rooms. So for now, we didn't like implement in the room yet. So we are trying to achieve our pre-testing on the simulation. We're doing big data for the data expansions because the big data is in hourly, year hourly. So it's a comparison of the default, the fixed data they have, and we're creating a more realistic way to using our semesters variation, use academic calendars to adding some like holidays and some holidays that only happen in school. And also we were creating a different occupancy in the weekdays. Also, for example, like for the final, people gonna not go into the lab maybe. So just trying to make the fixed data more realistic. And also changing the daily occupancy rate from the default. The default is always going to 100%, so that we're just changing to a more realistic way. So usually maybe only 50% at the most for the 10-seat room.
Yeah, okay. So for the current state and end goal for like our software pipeline, currently I'm using Sean's like synthetic occupancy data to prototype our pipeline because Kavia's entire setup is not, set up in the SimTigrate lab already. However, it is in the software pipeline available as an input to use our sensor data. So there's two modes of input you can use. Currently, we're just using the synthetic occupancy just to test the pipeline in general. This synthetic information is behavior informed. So we kind of start with the room scale hourly schedule, and then we distribute occupancy positions across the room and prioritize desks because that's where students and people tend to work at. For some of the logic constraints, the northern desks, which we'll show an image in the next slide, have a more stable occupancy, and then the west and south computers carry the most occupancy. And then people kind of generally just float around the room if they're not sitting at a computer. And then obviously our end goal is to replace these synthetic inputs with live sensor detected 2D positions, which we'll be able to get, I believe, soon. And then the outputs from this software pipeline will inform the schedules and the Grasshopper HVAC pipeline that Roger's working with. So kind of for like a pipeline connection, this kind of just shows like where we're sitting at, where I guess the software is sitting at. And essentially for the input side, it's Cavia's data, and then we process it, and then we turn it into the L0 through L4 occupancy abstraction layers. And then the output is a CSV output, which will then be input into Grasshopper. So I guess it's kind of like what the script generates. So it generates the 4 levels of granularity that we've been kind of talking about over the presentation. And this is kind of an example of what the input looks like in the CSV file. For the synthetic data, it's just a fraction, a rate at intervals of 30 minutes. And this fraction is based off of a nominal occupancy. So like, 10 people, you like set a number of people, and then it determines how many people are in that room at a given time from the schedule. And at the bottom is what we're going to be using for the actual,
So the fraction is out of how many, out of 100% occupancy, that's possible?
Yes.
Okay.
Yes. And then the bottom is what the actual like physical, like real data would look like. So it has the human count and it has the positions, kind of like what Kavya showed earlier from our sensors. And then these are the outputs of the script. So we can see from here, we have the L1 through L4 granularity. So we have the presence hysteresis, the total count, the occupancy fraction. And as you can see in the bottom image, we have the total heat gain from people. So, their metabolic heat gain, the equipment heat gain, and that kind of totals up and allows us to be more informed with the higher levels of granularity. And then for how we're gonna map the data, we had a 3D capture using a Cubix Vista, and it generates a point cloud, which we use to kind of build our digital twin and to model this simulation. So this is, I have an image in the bottom right where we have a visualization of how people move throughout the room. And then we can use this to determine what zones they are, if they're sitting at a desk or if they're sitting at a computer. And yeah. For real-time uncertainty and validation, for our current version, we stabilize the occupancy before we process and output the results. So we convert our schedule into a 5-minute timeline where we have time steps at intervals of 5 minutes. And then we fill in the temporal gaps in our data by resampling to interpolate the results. And then we do rolling smoothing to reduce like random noises that could occur due to sensor uncertainty and like random sensor errors. And then we apply presence hysteresis. So like, brief zeros of like maybe a sensor just stopped detecting someone for a brief time, doesn't immediately flip our occupancy state. And then for some of the next steps, we plan on having like future validation.
12 minutes, just.
Yeah. We have future validation, maybe like you can check in through a QR or something so we can track the actual count of people in the room.
So I've done the simulation from L0 to L4 in Grasshopper, mainly using Honeybee. And the general workflow is like I apply the CSV schedule to the program. I'll explain later what the program is and the HVAC system. In this case, I'm using the Honeybee Ideal Air component, and we apply the program and the HVAC system into the model. And after simulation, we get the results. So what is a program? A program is where you can set parameters regarding people, equipment, lighting, ventilation, etc., and apply them to the rooms. And as you can see, like this is a people component, lighting component. And you can set the occupancy schedule, activity schedule. So yeah, so the data in CSV just goes in here. Now this is the L0, which is the base case. I'm going to go through the program inputs. First, the occupancy is fully occupied at all times from 6 a.m. to 7 p.m. Monday to Friday. By saying this, I'm not saying that's the real occupancy, but I'm just saying that's like in the design of HVAC system, it is assumed that the occupancy is like that. So these inputs are actually, let's say, assumptions. And as we progress from L0 to L4, because we have more like higher granularity data, these assumptions will be changed. So yeah, this is the yellow thing is the UI of the rooms, and the bottom we can see the from left to right is the people gain, like the ventilation heat and the ventilation energy and the electrical equipment energy. So from L0 to L2, we have divided the zones, so we can see that it's just the data is just consistent among all zones. Then we jump into L1. So this is where occupant, like the inputs for occupancy changes. We set it as occupied or unoccupied. If it's occupied, we still assume it's the maximum occupancy. I forgot to talk about the activity. Now we assume they're all
Roger, sorry, I have to, because we need to start the next group on time. We need to jump to the end.
Oh,
Yeah, sorry about that.
so I want, I mean, like the people getting ready dropped because of like a feed occupancy, like L2, we changed the occupancy to people count, and the ventilation airflow rates will vary according to the occupancy and as well as the HVAC availability. Jump to the end. So for L3, we have zoning. You can see that there's still from now there's like difference between rooms.
So let's move to the question. Sorry, we just don't have any more time. I apologize.